Lastly, we're going to talk about the experimental setup and conditions for the workshop that we're going to work. As for the configuration, we're going to work with a cylinder on plane configuration using a 40 by 10 millimeter specimen and a 50 millimeter radii pad, both parts with a thickness of 4 millimeters. The material used is going to be an aluminum 2024 T3, which has a Young modulus of 72.1 gigapascal and a Poisson coefficient of 0.33. This material is going to be assigned to both parts. And lastly, for the load ratios, since we're working with fatigue, we have to have the varying loads. So the ratio between the minimum and the maximum actual stress, the actual bulk load, is going to be 0.1, and the minimum, or well, the ratio of the tangential load is going to be -1. Right now we're going to start with the workshops. First of all, we're going to consider some simplifications on the model. First of all, as you saw, the model is symmetrical about the actual axis of the specimen. So we're going to draw only half of the configuration, half of the specimen and only one of the paths. Also, as we're going to work with fatigue, we have varying loads, but we're not going to use explicit simulations, but we're going to analyze it as a quasi-static simulation. And lastly, on the figure you can see the crack that was developed, the crack formation on the configuration. As you can see, it is semi-elliptical, showing that a 2D model can be developed, and also it grew more in depth than through thickness, showing the presence of plane strain behavior in the crack. All of these parameters are going to be used in order to create the model, to define the steps, and also the mesh. So we're going to start with the simulation, opening Abaqus. In here, the 4 models are going to be used either for the meshing part, for the meshing explanation, or for the simulation part. In here, I'm going to go for the line part, for the line model, just to show the starting point of it. So we created 2 parts, or there are created 2 parts, a cylindrical path and, well, a plane. These parts are both defined, are both created with the dimensions that I explained earlier. As you can see, the path is going to be 10 by 10 with a radius of 50 millimeters. Then for the property part, I defined the material. So as you can see in here, I have defined the aluminum 2024 P3, which has these properties. I have defined the elastic behavior with a Young's modulus of 22,100 and a Poisson's ratio of 0.33. The value of the Young's modulus is mostly because, as you know, Abaqus doesn't work with units, so all the units are going to be, the force units are going to be Newton, the dimensions are going to be in millimeters, so the stress is going to be on megapascal. This on the assembly, as you can see, I have assembled it as is shown in the figures. Just the path over the plane on the middle. Okay. For the step, we are going to make another simplifications. We are going to divide the steps, or we're going to divide the simulation on 3 steps. We're going to have a first step called pressure, which is just going to be the application of the compressive force. And since it is going to be the most delicate part, there are many simulations cannot work if this part doesn't work correctly. So we are going to do a little adjustment to it. We're not going to do it automatically by Abaqus. So we're going to make it last half of the simulated time. And then we're going to have another two steps called max and min. As you can see here on the graph, we have the three steps. So here in Abaqus, as you can see, I have, well, the initial step, which is always created there, and I created three different steps. Then we're going to talk about the contact parameters or the interactions. Here, we're going to develop some different behaviors. These are going to work well for threading. You can use other parameters, but these are going to be the ones that give the best results. Okay. For the loads, we're not going to define them as it is on the real-life configuration. First of all, we have three boundary conditions. We have a symmetry boundary condition on the bottom part of the specimen, because there is a symmetry in there, in the y-axis. And then for the min step, we're going to place it at minus 10 megapascal. But these three configurations are based on the same principles, which is going to be having the model divided into zones, a far from the contact zone and a near the contact zone. As you can see in here, we have a phase partition where we're going to have a different meshing near the contact zone, and then we're going to define a different mesh farther from this part. In here, we have three different seed sizes for the mesh. We're going to define a 0.5 millimeter for the farthest edges from the contact zone, then a 5 micrometer element on the contact edge, and then the other seed depends mostly on the type of methodology that we're going to work with. As you can see in here, on the farthest part of the mesh, we're going to have really big elements. They are 0.5 millimeters, and here near the contact zone, as you can see, they are really small. Then they are going to be, in this case, 5 micrometers in size. However, we're going to have three different methodologies. As I guess you have seen, the different models of the Abaqus file are named box, line, and vbox. These are going to be the three different mesh methodologies that we're going to work with. These methodologies depend mostly on a different type of phase partition. As you can see here, we have like some boxes for the box method. In the line method, you can't see anything, but it is mostly because there is a partition, a line partition here in the contact zone. And then for the vbox or variable box one, we're going to have smaller boxes that we're going to see next. So for the line method, the contact zone is going to be divided only on the surface, as you saw. In this case, I used datum planes in order to partition it. Then for the mesh, as you can see, we have something quite similar, but if we go further into the contact zone, you can see that all the elements are constant. They are just the same, they are organized, and it is a quite big area with those elements. The core differences between these methodologies are that the line method is a multi-purpose method. It can be used whenever you want if what you want is just to analyze the contact surface. Between all of them, it is the most accurate. It's the most accurate one with contact stresses. And then the box and the variable box methods both are useful if the soft surface analysis is required. The VBox has more accurate contact stresses, and it is used if, for example, you need contact stresses, but you need other calculations with soft surface stresses, but not so accurate. Meanwhile, the box method has a little bit less accurate contact stresses, but its soft surface stresses are way more accurate than the other ones. Also, another thing to consider is the computational time. As you can see, the box method computational time increases exponentially really fast compared to the other ones. So, for example, the use of the box method depends on the accuracy of soft surface stresses and also how much time you're willing to pay for this precision on soft surface stresses. Meanwhile, the line and the VBox method are quite similar for for smaller, for example, for a 2 micrometer minimum element size, we're going to have the VBox being a little bit slower than the line method, but normally the VBox is going to be a little bit faster. And as I said, it's going to work better if you need some subsurface analysis. Once we have done this, we can simulate. But prior to this, I'm going to explain you something. Here, for example, in the fretting model, if I enter to the parts, plane, and sets, you can see that I have created two sets. One is called contact, and the other one results. These sets that I have created here are going to be used to get the results, that we want. Contact, in this case, is just the line, the fine line of the contact between the specimen and the pad, and the results are going to be all this area around here. This area around here is going to work to create the field outputs later. But this contact one is going to be the one that is going to give me the real results that we want for our verification. So we can now simulate. In this case, if I monitor my simulation, I have 104 increments on step 1, 54 increments on step 2, and 54 increments on step 3. Also, I have developed some warnings in here about the two-dimension models, the Lagrange convergence, about the MPC, and some boundary conditions, but they don't really matter. Doesn't mean that the simulation has an issue. The simulation is completely okay. And in this case, for me, the simulation lasted around 6 minutes. It depends, it could be more, it could be less, depending on your machine. So we can go here to see the results.